So, in this presentation we're going to look at some inverse Laplace transforms. Now these are sort of simple enough, like you will get to a higher standard later on, but this is sort of an introductory level inverse Laplace transform type stuff. Now just as a remark, we're using tables that you can get on my website, mathsresource.com. Now, the first one is find the inverse Laplace transform of g of s. Now actually conventionally functions are written in as f of s rather than g of s. The reason I actually just use g of s is because on the tables I uses f of s, and so I'm just sort of making a distinction between given in the question g and f, some sort of structure from the formulae from the tables, the formula sheet. So that's just the sort of reason why I sort of switched to g of s. Anyway, so what we got here is, this is the Laplace transform, s minus 1 over s squared minus 2s plus 2. Now, what we would normally, the first port of call here would be to see if we could sort of factorize that, okay? S squared minus 2s plus 2. Now, in this particular instance, there's no easy factorization from that. Okay, you can try it out yourself, but what we're looking for is essentially natural numbers, or things like a half or a third or something like that, just for the level we're at the moment, and that's not what we would get there. So there's a different approach we could take, and what we're going to do is rewrite the denominator as follows. This is a sort of thing called completing the squares. So if you just notice here at the start, we have 2s minus s, or sorry, s squared minus 2s, s squared minus 2s. So what would, if that was a square function, as in what would it be? What would it be? So what would be the rest of it here? If this was something, if this was s plus a squared, what would it be? Well, it would be plus 1. Okay, how did I know that? Essentially what we're saying is this is s minus a squared equals s plus a equals s minus 1 squared. Okay, how did I know it was minus 1? Well, if you square s plus a, you will get s squared plus 2a, or a plus a, s plus a squared. Okay. Just as a sort of, yeah, I'll sort of come back to that. That's actually sort of, it's sort of very useful to remind yourself of this sort of stuff here, actually. So what we're going to say is that s squared minus 2s plus 2, we're going to sort of split it up into two parts. We're going to call it s squared minus 2s plus 1 plus 1. Okay, so I have this component here and plus 1. So what I can say further is that we can call this s minus 1 squared plus 1. Okay, s minus 1 to be squared plus 1. So I can re-express that as that. Okay, now just recall the numerator of the function. It was s minus 1 over s squared minus 2s plus 2. Now unfortunately that was not a clue for the s minus 1 stuff. This is our function here now, s minus 1 over s minus 1 squared plus 1. I'll just write it down here again. By the way, you can use full screen mode on YouTube if you're finding this a bit hard to read. S minus 1 over s minus 1 squared plus 1. What I'm going to say is I'm going to write this in the form f of s minus 1. So this is, we're going to use a shifting theorem here. Okay, so we write this as a function of s minus 1, where s minus 1 is equal to s minus 1 over s minus 1 squared plus 1. Okay, now what I'm going to do is actually just skip to the next slide and look at the tables. And what I'm going to do here is, this is the statistical tables I'm using, and I'm particularly interested in this line here. Okay, so what we have is the Laplace transform of e to the power of at f of t is equal to the f of s minus a. Okay. Now, in this particular instance, always be mindful of this. When you get sort of stuck, sort of see what you can find in the tables. I'm letting this equal to f. I'm going to let a equal to 1. We have a function that I can call f of s minus 1. Okay, where a is equal to 1. Now, what I'm going to do is find the inverse Laplace transform of that, which is e to the power of at. Well, a is going to be 1, so this is e to the power of t. Okay, but the other part is f of t. And what is f of t? Well, the f of t, so the inverse Laplace transform of f of s is f of t. Now, what we have is f of s minus 1. We don't have f of s just yet. So, just look at this here. What we're going to do is replace each term here, f of s minus 1. What we're going to do is replace each term with f of s. Oh, sorry, s minus 1. We're just going to replace it with s. So, s minus 1 over s minus 1 squared plus 1. Now, what we're going to do is replace s minus 1. So, top line here, s minus 1 squared, s squared plus 1. Okay, that is f of s. Okay, if this is f of s minus 1. So, what we have here now is we have a, we have f of s, and what we're going to do is get the inverse Laplace transform of that. This is a pretty simple exercise there. Okay, use that one there. Now, unfortunately, on the tables, this is the tables, by the way. This is just a sort of section from my mathematical tables. This is the Laplace transform over here. Sorry, this is the Laplace side over here, and this is the time domain f of t. So we have this expression here, s over s squared plus 1. That's essentially s over s squared plus a squared, which will go back into the form cos of at. Now, just to be clear about something, this is why the tables gets confusing. So I'm not going to sort of work on it anymore, but usually what I might do is actually try and just try and say that that is a different a to what we have been dealing with previously. Although it turns out they both have the same value, it's just the notation is different. They actually have the same notation for two different things, but they have the same value. Just watch out for that, essentially, is what I'm saying. Particularly when you're working with like these tables. So, f of s is s over s squared plus 1. The inverse Laplace transform of that, therefore, is cos of t, or cos of 1t. Okay. Now, the answer we're looking for is e to at. Now, this is the original at, not from that cos thing. This is the answer we're looking for. Okay, this is g of t. And we found e of at earlier, and now we have f of t. So there it is there. That's our answer. E to the power of t cos t. Now, just as a remark, actually, properly you should write in t greater than or equal to 0 as part of your answer, because just as it states precisely the time domain that this answer is valid for. So e to the t cos t, t greater than or equal to 0. Okay, so that's the first one. Now what we're going to do is have a look at the second one, find the inverse Laplace transform of this expression here. What we're going to do actually is just sort of remark that we can sort of, let's go to the tables actually. No, let's go to the tables here. So what can we do here? What we can do here is actually split it up into two parts. We have an expression here, s over s minus a times s minus b, and we have an expression just above it, 1 over s minus a times s minus b. So we're going to use those, because essentially all we need is the a and the b component. So what we're going to do here is see if we can factorize this. Now it turns out this is in this particular instance, it's a pretty easy factorization. S plus 6 s minus 1, and that's in the form s minus a s minus b, okay? Or vice versa, actually. I might sort of switch the order there. Just to, you'll see why in a second, but essentially it's in that form there. So there we have it there, s plus 6 times s minus 1. So what I'm going to do here is re-express the entire thing out as these two terms here. So s over s plus 6 times s minus 1, 2 over s plus 6 times s minus 1. So we're just sort of having the form, the addition of two, the sum of two Laplace terms. There we have it there. So what we need here is a and b, and that will give us our answer pretty quickly. All we have to do is sub it into the what we have. Put in essentially all we have 1 over a minus b times e at minus e to the bt. Something similar down here. The only thing I'm going to do here is just to sort of remark that we had plus 2 here, so look out for that. So I'm just going to put in here instead of that, just I have a 2 here instead, so I'm just going to put a 2 there as well. Just to sort of multiply by the constant it was used. Yeah, so let a equal 1, b equal to minus 6, okay. Now there's a term here, a minus b, okay. A minus b is equal to 7, okay. So I'm just going to sub in the values here. 1 over a minus b, a over a minus b times e to the at, there we go, plus minus b is minus 6, so that's plus 6. Plus 6 over a minus b to e to the minus 6t. So essentially, all I'm doing is just subbing in the values there. A over a minus b is 1/7. B over a minus b is, or minus b over a minus b is plus 6 over 7. And e to the at is e to the t, and e to the bt is e to the minus 6t. This is really easy. Just actually, I'm just adding up these 4 terms here, putting an a into the 4 terms and just adding them up. That's all I've done here. Let's just add up like with like. We have 1 over 7 et to the power of et, 2 over 7 plus 2 over 7 to the times e to the t. Let's just add them up there. 6 and minus 2, add them up there. 6 over 7 minus 2 over 7 times e to the minus 6t. This is just tidying it all up. So we have 3 over 7 e to the t plus 4 over 7 e to the minus 6t, and again t greater than or equal to 0. Just put that in there as well. Finally, one more, and we'll finish off with a nice easy one. This is why you always factorize. Don't go anything first. Okay, factorize the denominator. So we have s minus 2, and if we factorize the denominator, we get s minus 3 over s minus 2. The s minus 2 values cancel out. So we have 1 over s minus 3. This is a very easy one. There we have it there. Straight from the tables. This one here. So we have 1 over s minus 3. The answer therefore is, a is necessarily 3. So e to the at is our answer. So the answer is g of t e to the 3t, that one there. And once again, t greater than or equal to 0. So that's enough of this. We'll call that a wrap.